Okay, gang, I'm going to take you through how to find a one-sample z-interval for a population proportion. The last video talked about what a confidence interval is in very broad terms, and we talked about that in class a little bit, but today I'm going to talk to you about how to actually find the numerical values that go with a z-interval. In order to find these critical values, or these confidence intervals, it's all going to be based upon something called a critical value, which the statistical symbol for that is z star. A critical value is simply a z-score, and it is a z-score that corresponds to a certain confidence level. So when we say we want to be 90% confident, that means when we create our interval, we want our interval to contain 90% of the data, which means this. Now, if I were to ask you to find the z-score based on this picture, you should know how to do that because you know how to do inverse norm and you know how to find a z-score. And if you were to find this z-score, you would get a z-score of 1.645. That is the critical value, the z star, that corresponds to a 90% confidence interval. Simple enough, right? What if we wanted to be a little bit more confident? What if we wanted to go to 95%? So let's change this and we go to 95%. That means this number here is no longer 5%. Now it's 2.5%. And this number here is 2.5%. The z star value that now goes with this new number is no longer 1.645. Now the z-score is 1.96. And that's actually the most common one. That's the one we use more than anything else in statistics. And then finally, the third one that we use a lot is what if we want to be even more confident? What if we want to capture 99%? If we wanted to capture 99%, that means this area out here is 0.5%, and this area out here is 0.5%, and this z critical value is not 1.96. Now this z critical value is 2.575. Okay, so those are the three critical values that we use more than anything else in statistics, and they all come from those three confidence levels, 90%, 95%, 99%. There are other z critical values that we can use, and you're going to find those when we start looking at the bottom row of table C in your textbook, and we'll show you how to find those tomorrow. All right, now that we've talked about that, let's talk about the steps for doing a confidence interval. Step number one, you have to state a population of interest. Tell me what it is that we're looking, what it is we're working on here. What is the population of interest in this case? And you want to state that very clearly. Secondly, you want to address assumptions. There are three basic assumptions that we want to use and we want to address. First, it needs to be randomly assigned. Secondly, the sampling distribution needs to be normal or approximately normal. Now, there's a bunch of different ways. We talked about this in the last chapter. How do we know if a sampling distribution is normal? Well, the easiest way is if it's given. It just flat out tells you it's normal. That's great. Or if there's a large sample size. Okay, if there's a large sample size, then it's approximately normal. We know that. And also, in the third option, if you're given a set of data, you can graph that data. And if the data that you're given is approximately normal, then it's safe to assume the sampling distribution is as well. The next step, and you also have to know the standard deviation. Sorry, wrote that down. The third step is you have to name the interval. Before this semester is done, we're going to learn a whole bunch of different confidence intervals. And so when you're writing out a problem, you need to tell the grader what type of interval you're doing. And you have to be very specific. So we have to name the interval. And then next, find the interval. Actually state it. This is where you actually do the math. You calculate the interval and you state the numbers. And then finally, you write your conclusion in context. And now here on the screen popped up the word panic. Mr. Lachelle and I kind of have a different philosophy on this. I use the word panic to help me remember how to set these things up. And he doesn't like acronyms, so he doesn't use this. Either way is fine. But I use the word panic because it reminds me population, address the assumptions, name the interval, state the interval, and then draw the conclusion in context. So it helps me remember the 5 parts. He just uses state planning to conclude, which is the exact same thing, just a different way. So either way is fine. When you're calculating a standard deviation of a statistic, when it's being estimated from data, the result is called the standard error. So that is the standard error. The standard error is the standard deviation of a statistic, which is basically the standard deviation of a sampling distribution. Here's the formula that we're going to use for that. So you're going to want to write this down. And let's break this into its different pieces. First, where'd it go? First, let me go back, is this part, p hat. P hat, that's your point estimate. If you take a sample and you figure out a proportion from that one sample, that's an estimate. So we start with that. Next up is the Z critical. That's your critical value. That's the one that we just talked about on the previous slide. Which number are we going to use? It depends on what confidence level we want. And finally, we have this formula, this part of the formula, which is the standard deviation of the statistic. We call that the standard error. And if you put these two things together, the Z critical and the standard error, that becomes the margin of error. And then finally, if you look at the whole thing, that's called a confidence interval. All right, so I've done a lot of talking. Let's show you an example. Here's the first example. The present packaging system produces 10% defective cereal boxes. We're going to use a new system with a random sample of 200 boxes. It had 11 defects. The question is, does the new system produce fewer defects? Well, let's construct a confidence interval to answer this question. So here it is, all written out. Notice that I am using panic. So my population of interest, p hat. The p hat that we had was 11 out of 200, which is 0.055. We want to address our assumptions. First, it was random. It stated it in the problem. So we say we have an SRS of cereal boxes. We address normality, n times p, so 200 times 0.10 and 200 times 0.9. They're both greater than 10, so we can assume normality. And we address independence. Assume more than 2,000 cereal boxes are produced. We can assume independence. This should look very familiar to Chapter 7. We did the exact same things. Only thing I added here was the randomness. Name the interval. We are going to construct a one sample, 95% confidence interval for the population proportion. You need all three parts. This is a one sample. That's the first part. 95% confidence interval. That's the second part for the population proportion. Then state the interval. This I use my formula that I just gave you for. My point estimate was 0.055. My critical value, since I'm doing a 95%, is 1.96. And the standard error, using the formula from the previous slide, was 0.016. Multiply that out, add and subtract, and you get your confidence interval. And then here's your sentence that you have to remember. We are 95% confident that the true proportion of defective cereal boxes is between 0.0234 and 0.0866. There is sufficient evidence to conclude that the new system produces fewer defects. And there's that formula to find the standard error. All right, I went through that really fast. I'm going to do one more example, and then I'm going to let you try one. Here's the next example. The Gallup Youth Survey asked a random sample of 439 U.S. teens whether they thought young people should wait to have sex until marriage. Of the sample, 246 said yes. We want to construct and interpret a 95% confidence interval for this proportion. So here's our steps. First, population of interest, p hat. 246 out of 439, that's 0.56. Address the assumptions, three assumptions. First, SRS. Yeah, it said it was an SRS in the problem, so we do have an SRS. Normality, sure, we do P times N, so 439 times 0.56 plus 439 times 0.44. Both of those numbers are greater than 10, so therefore we may assume normality of the sampling distribution. We can also safely assume that there are more than 4,390 U.S. teens in the country. This would allow us to assume independence. Then we can name the interval. The one sample, 95% confidence interval for the population proportion. And here's our formula for our standard error, which we can then plug into our interval. 0.56 plus 95% is 1.96 times 0.024. Add and subtract, you get 0.514 to 0.606. And now we can say we are 95% confident that the interval from 0.514 to 0.606 successfully captures the true proportion of teenagers in the US who would say that teens should wait until marriage to have sex. All right, so I went through those really quick, but I gave you 2 examples. I want you to do the next one. This one's for you. Bring it to class tomorrow. Make sure you write it up. I am going to pick a few examples at random, put up on the screen, and critique. Good luck. I will see you tomorrow.